Yeah, am I audible?
Yes, sir.
Okay. Yeah, I will send you the detail of the syllabus of the course. Okay, for the first semester exam. Okay, by today evening. And whether 7th of March is a instructional day? Yes. Can anyone confirm? From 8th of March, the class, the exam has started. Is it so?
Yes, sir.
So 7th March is an instructional day, not holiday.
Sir, most of the lectures are ending by this week, but like some of have, like in the CS we have lab. Instead that I don't think there is any lectures on the next week.
Okay. So that's a CS lab is Arnav's lab, right? 2 to 4.
Yeah, it's from 2 to 3.
2 to 3. Okay. Okay. So because I have to find out the window where this exam time can be put up. Okay. Okay, I will inform you. I mean, like by today evening, surely will get an email. And till the last uploaded lecture, you can imagine that. Okay, the syllabus of the mid semester exam. Okay, so today's lecture you can exempt only because see, after this chi-square distribution is a part of the previous lecture video. If you have looked on that this lecture number 12 on the YouTube, this is chi-square. So I'm just explaining here. So if you have any doubt, you can ask. Okay, and so chi-square distribution is a part of that. Okay, right. Okay. Now, so let's start the lecture. So you are able to see the screen, right?
Yes.
Yes, sir.
Okay, okay, fine. Okay. So this chi-square distribution is a natural outcome of the normal distribution. Okay, and it has applications in the statistics. Okay, there you will find more applicable in realistic manner. Okay, so I'm only here going to most of the things I'm going to deal with the theoretical aspects. Okay, how that behaves if n is increasing, and what are the properties of this, and how to look at the chi-square table. Okay, there's a table also associated with this, how to identify some point means like which we have done in similar manner as for normal table and so on. Okay, so those things we try to address here. Okay, now if you look at the if you have gone through this definition, the first line, what it says is if you have n number of independent standard normal variate. Okay, what does that mean? This mean is zi follows the normal distribution with mean 0 and 1 is variance, or you can say standard deviation with I equals to 1 to n. Okay, so first of the thing is each one is independent and they are standard normal variate. Okay, so that's in a short way. Standard normal variable is nothing but a normal variable, normal random variable with mean 0 and standard deviation 1. Now you scared each one and then put the sum. Okay, n number of independent standard normal variate, you each one you scared. So still see, you have, if you recall that if x and y are independent, then so is their functions. So z1 square, z2 square, and so on, zn square, all are also independent random variables. We don't know standard normal or what, we will try to identify it little later. But if you squared all the random variables, they are also independent because of the independence of zi's. Okay, now so once so maybe it is I don't know whether it is, if we are going to able to identify directly the variance and the mean of this, but we can try to address. Okay. Okay, so if you define that x is a squared of this and you have n, so this is why here you will see a notation. So this notation we are going to define as chi. I think you are mostly familiar with this mathematical notation of chi. And n is stands for the number of independent standard normal variate you are taking, and which is also known as n degrees of freedom. Okay, and 2 here is stands for this. Here you have squared this, so this is stands for 2. Okay, so if somebody is giving you x follows this chi n square or chi 26 square, okay, so n means you are summing squared normal variate 26 independent. Okay, 26 independent standard normal squared of standard normal variate. This is what it means. Okay, right. Now we will try to see how to identify the CDF of this. Okay, that we will try to do that. Now, so here is the one plot with n degrees of freedom for this chi-square density function. Okay, so you can see when n is going large, n equals to 1, n equals to 3, n equals to 10, and if you go further, n equals to 50 and so on, it is again going to converge towards the normal distribution. Okay, and you will get this theoretical base that which will make you confident. Okay, that mathematical ground. Okay, that's known as central limit theorem. Okay, that will give you the base to say that, oh, if you have any continuous random variable or a discrete random variable on the large, when you on the large extent, is going to be approximated by a standard normal variable or normal random variable. At least it will give you some rough idea about it. Okay, right. Now, so this is so what, how to identify the distribution of this chi-n square is, you have to work out the MGF, moment generating function. Okay, so let me try to uh, do this. Okay, So what we are interested in, x is following the chi-n square. Okay, where this is nothing but summation I is equals to 1 to n zi square, and each zi follows the normal with mean 0 and 1. I is equals to 1 to n. Okay, so to identify the density, what type of random variable, or is it a special type, so that we already know. So first we will try to identify movement generating function. Okay, so let's try to find MGF of x. Okay, so if you try to write down, it's going to be expectation of e to the power tx, and this is equals to e to the power t chi-n square. Chi-n square is summation of zi square. Summation I equals to 1 to n zi square. Okay. Now this is equals to, I hope you agree that it's going to be product of I is equals to 1 to n expectation of e to the power t zi square. Okay, why? Because they are independent. So you can write the sum as also e to the power t zi square, tz1 square into e to the power tz2 square, and so on e to the power tzn square. Okay, I think expectation of this. Expectation is missing. Okay, now each one zi is following the standard normal variate. So if we identify the distribution of zi square, it is easy. MGF of, or you can say MGF of this. Okay, right. So I'm going to take the particular case. So now let Z follows normal distribution with 0, mean, and 1. Okay, then I will try to look at its mz of t. Okay, that's going to be expectation of e to the power, not z of t, I think, and x, or you can say nth of x. Let's say it is going to be y equals to z square. I'm interested in my of t, so e to the power t y, and that's equals to expectation of e to the power t z square. Now this is equals to 1 upon square root of 2 pi integration minus infinity to infinity e to the power t z square time e to the power minus z square by 2 dz. I hope there is no problem to follow this. Right? We know if you have expectation of function of z, how will you find out? You can take the help of the density function of the z random variable. Okay. Now if you further simplify it, so this is equals to 1 upon square root of 2 pi integration minus infinity to plus infinity e to the power tz square minus z square by 2. If you do all the stuff here, so you have this is going to be t minus, I'm just writing one more step, z square. All of you are agree with this. Now this is equals to 1 by square root of 2 pi integration minus infinity to infinity. I'm writing in a something e to the power minus z square time you have 2t minus 1 by 2 dz. Okay, I've taken the answer. Now this t is fixed. Okay, t is fixed. For a fixed t you are trying to identify, so you have to treat this t as fixed right now. Now let's denote, I'm going to denote a sigma bar square is equals to 1 upon 2t minus, this is going to be with minus sign, so it's going to be minus here, it's plus. Yeah, so it's not okay. So I'm going to define sigma bar square equals to 1 upon 1 minus 2t. Okay. Now here I think it's very clear. Sigma bar square is a positive quantity, and this will be positive whenever t is you have 1 minus 2t is greater than 0 and t is greater than half, right? Or t is less than half. 1 minus 2t, so t is less than. Okay, so 1 minus 2t is greater than 0. That's very important. Now, what it will do? So this will imply my of t is equals to 1 upon square root of 2 pi integration minus infinity to infinity e to the power minus z square by 2 sigma bar square dz. Okay. Now I'm trying to write down. I think it is very easy to follow many persons. I'm just multiplying and divide by sigma bar here, and integration minus infinity to infinity e to the power minus 1 by 2 z minus 0 by sigma bar square dz. And I hope this can be identified. Okay, this one can be easy to identify as a density function for a normal random variable with mean 0 and variance sigma bar square. So this is a density function, so this is going to be value is 1 that you can use. Okay, and that's equals to sigma bar. So what is sigma bar is? Sigma bar square was 1 upon 1 minus 2t. So sigma bar is 1 upon square root of 1 minus 2t. Obviously t is less than 1 by 2. Right? So this implies what? So this implies m z square t, this is equals to 1 minus 2t to the power minus 1 by 2. Now with all this story, if I go back and check m chi n square of t is equals to product of I is equals to 1 to n 1 minus 2t to the power minus 1 by 2. Obviously, this t less than 1 by 2 is going parallel here. Okay, t is less than 1 by 2. Okay, and this is going to be 1 minus 2t to the power minus n by 2. Now, if you try to write now, this is going to be now. I'm going to write it now. So it's going to be now this 2 is out, let's say 2 is out. So 2 to the power minus n by 2, you have 1 by 2 minus t to the power minus n by 2. Okay. Now, further, this is equals to 2 to the power minus n by 2, I can write 1 upon 2 to the power n by 2. Okay. And that another one is 1 by 2 minus t to the power minus n by 2. So I can take it in the denominator 1 by 2 minus t to the power n by 2. And t is less than 1 by 2. Now, can you able to identify it now? This moment generating function stands for which distribution? We have worked so far different type of distributions.
Gamma distribution.
Yeah, gamma distribution. Okay, with parameters alpha is equals to n by 2 and lambda is equals to 1 by 2. So once you know this is a gamma distribution with these parameters, and you know expectation of a gamma distribution was, yes, mean for a, so this implies expectation of chi and square. What was the mean? Alpha by lambda. Okay, that's going to be alpha by lambda. That's going to be n by 2 divided by 1 by 2. So it's going to be n. And what was the variance of chi n square, or means the gamma distribution, is alpha by lambda square, if you recall. Lambda square. So this is equals to n by 2 divided by 1 by 4. So it's going to be 2. So you have all the information. So chi-square distribution is gamma distribution with fixed parameter now. Alpha is equals to n by 2 and lambda equals to 1 by 2. And its mean is n and variance is 2n, 2 times. Okay, right. So MGF gives you almost all the information. Okay, once you are able to identify. Okay, right. Now, so I have discussed this. Okay. Now, like we have defined the 100 1 minus alpha percentile in case of normal variate. So similarly here also for the chi-square distribution. So since it's already okay, so this alpha here. So there was is if I recall, this is z alpha, if you recall. Now here is x square, okay, because due to this square is not for the making it positive. Okay, this 2 is stands for that chi-square, related to the chi-square. N stands for the degree of freedom. Alpha, what is alpha stands for is any number between 0 to 1. Okay. Now, the quantity, this x square alpha, what is the definition, is nothing but probability of x greater than equals to x square alpha comma n is alpha. Means the area covered right to the x square alpha comma n is going to be alpha. And what about the left is 1 minus alpha. The area covered on the left of the x square alpha by alpha comma n is 1 minus alpha. Right to the x square alpha n is alpha. Okay. Now let's try to, if you have to work out with the problems, how to use the table. Okay, that also we will try to understand. Yeah. So I'm trying to identify this first one. Chi square 26 less than equals to 30. Okay, I want to understand. So from here, what I can easily identify from here, first thing, what I am interested in, probability, this is equals to alpha. Okay, some alpha, or this is less than equals to, you can say 1 minus alpha. Okay, so alpha need to be determined also. Okay, n equals to, it is very clear that n equals to 26. Okay, so for which x square alpha, what is the approximate, is approximation comma 26 less than equals to, the x square alpha comma 26 is 30. From here I can identify that x square, this I am denoting this x square alpha comma 26. 26 is, and the degree of freedom is 26 because of this 26 here. Okay, and alpha needs to be determined for which value of alpha. So what is the value is 30 here. That's also fixed. So what is the area covered right to the, sorry, left to the 30? That's what we try to understand. Okay. Now this is the table. Let me zoom it. Okay. Now since, so this is the table for chi-square distributions. Okay. Now this column n values. This column will stand for n values. This is 1, 2. It is given till 30. Okay. And why till 30? Because of certain thing. I will let you know why n is equals to 30. And here some of the alpha values also has been given. Okay. Some textbook also have different more number of values of alphas are also included, means more number of columns also have it. But right now, what is the information or what is the table we have approximately, accordingly we have to react. Okay. So this is the table for probability of x greater than equals to this x square alpha n. So means what is the area covered right to this x square alpha n. This is what it is giving. Okay. Now I just identify n is degree of freedom is 26. So I certainly look at n equals to 26. In that row, I have to look at where the values is means either 30 or lies near to 30. So there are two values 15.379 and 38.885. Okay. So 30 will lies in between this. Okay. So what this gives you an idea, if you only want so 30 will lie between here. So what means the corresponding values of alpha means like what is the probability that this will lie between here is going to be between 0.05 and 0.95. So this is what it is giving, probability of x greater than equals to 38.885. Okay, 38.885. If you go with this column above alpha equals to 0.05, that's a probability. Another for x greater than equals to 15.379. This is 3.79 between this. Okay, so you have to choose these two. 0.95. So certainly probability of x greater than equals to 30 will lies between 0.05 and 0.95. These are the values that only you can tell from here. Okay. Now also see, you can also choose the approximate one because 38 is lies very near to 30 then 15. Okay, 30 is lies very close to 38 then 15. So it is almost here is 0.05. That means like, okay, just a little more than that, or I don't know what we can say about it. Now, so okay, so almost near to 0.05. Now this is a function. This is chi2s CDF. If you try to look at this, okay, this is the function in MATLAB. Okay, sorry. Okay, this is a function which you can try. So where the first parameter stands for the x square value, okay, and the second parameter for the this degree of freedom. That will give you CDF. Okay, please note that this is CDF, means probability that x is less than equals to x. The distributions, cumulative distribution function. What you are interested in, the negative of it. So 1 minus 0.9 is 0.1. So, okay, so because you are trying to identify x greater than equals to 30, let's try to approximate. So it's going to be 1 minus 0.9, it's going to be 0.1. Okay, right? Now, similarly, similarly, the B part, you have x square point, what is the value of this? X square 0.0515. Yeah, it is very easy to. Okay, so 15 is stands for the value is n is 15. So 15th row you have to take C, and for alpha equals to 0.05. Okay, so alpha equals to 0.05. This is the column, and 15. So this is the value of x square, that x square 0.05 comma 15, 24.996. Okay, right? So if you have any doubt, you can ask. Okay, let's go further. So this is that I think two examples are enough for looking at the table. Okay, right. Now let's take some practical example. Suppose that we are attempting to locate a target in 3D space, and that the three coordinate errors of the point chosen are independent normal random variables. Okay, so three coordinate errors of the point. are chosen are independent normal random variables with mean 0 and standard deviation 2. So if you denote xi as for the ith coordinate error of the point, okay, so each xi will follow the normal distribution with mean 0 and standard deviation is 2. Okay, so 3 coordinate error, okay, less, okay, fine. Okay, now find the probability that the distance between, find the probability that the distance between the point chosen and the target exceeds 3 meters. You know distance formula, right? Okay, and target is, you can look at that like a origin. Okay, that's your target. Okay, so from the origin, that's an error, your distance you can find out. Okay, so you know x1 square plus x2 square plus x3 square, three coordinate errors. So distance formula, you know, x1 square plus x2 square plus x3 square, if you denote xi as the error in the ith coordinate, and this is we are going to denote by d squares because of the distance. Now it is given that xi follows the normal distribution with 0 mean and 4 is the variance. So certainly we can convert each ith coordinate error in the standard normal variate by taking x minus mu by sigma. So xi minus 0 by sigma is square root of 4, that's 2. Okay. So what we can do is we can rewrite this d square, this one as d square by 4 is equals to x1 square by 4 plus x2 square by 4 plus x3 square by 4. Why? Then it will follow the chi3 square distribution. Okay, because they are, see, each coordinate errors are independent. Okay, so these are independent normal variate. Okay, now, and chi3 square, now you know this will follow the gamma distribution with alpha equals to 3 by 2, so 1.5, and degree of freedom is lambda is 1 by 2, that's a 0.5. You have every information. Okay, now what you are interested in is the probability that the distance between the point chosen and the target exceeds 3 meter. Okay, so we are interested in this d square or chi3 square is greater than 3. Okay, right? So we are interested in this distance is 3, so squared is what? This is 3 meter is 9. Okay, d squared, so d is the distance, so this is d is 3, so it's going to be 9. So d square greater than 9, we are interested. Okay, so we can certainly transform the information in the known thing. So d square by 4, because we know d square by 4 follows the chi3 square distribution. Okay, so we have transformed the information in the known thing. So this implies chi3 square is greater than 9 by 4. So 9 by 4 is what? 2.25. So if you try to identify this, what is the value? You have to certainly look at the chi-square distribution table with row number is 3 and equals to 3, and where this 2.25 is live. Okay, and if you go back and check, okay, so you have here just a minute. Yeah, so 3. So 2.25 will certainly lie between 0.352 and 7.815. Okay, so or if you want to find a good approximation, you can use this function chi2 serial. Okay, right, so choice is yours. Okay, so based on the table, okay, the probability will lies inside the interval 0.05 to 0.95. Okay, so this is why here, if you look at, okay, If you look at here, so it's going to be give you the interval is 0.05 to 0.9. So that's a probability. The distance target exceeds 3 meter. Okay, right? Now it's a very special case. If you try to attempt to locate a target in two-dimensional space. So earlier you were having in the dimension of 3D space. Now you are in the dimension of two-dimensional space. Okay, means this coordinate error will not be there. Okay, only two-dimensional space. So you will have again will similar formulation. You have chi2 square and which will follow the gamma distribution with 2 by 2. That's a 1 comma 1 by 2. Okay, so this is this implies this gamma. This is going to be d square by 4. This chi2 square is nothing but the gamma distribution with parameter alpha equals to 1 and 1 by 2, and which you certainly know this gamma distribution with alpha equals to 1 will follow the exponential distribution. So this is exponential distribution with parameter lambda is 1 by 2. You have all the information about it. And now, and you know the distribution of the exponential that exponential distribution random variable. Okay, so you know the information, so it's very simple now. D square greater than 9, d square by 4 is greater than 2.25, and you know, if you recall, it's going to be probability of x greater than equals to x in this case is going to be e to the power minus lambda x. So it's going to be 2.25 by 2. Okay, x equals to 2.25. So it's going to be approximately 0.3247. Okay, right. Any question? What does that mean, Kripal?
So in the previous example, we had a very large range of probability, like while looking into the table.
Yes, we have this 0.05 to 0.95. Yes.
So like having such a large range, won't it be like physically insignificant because like what am I going to
It will
infer from
not
such a
be.
large range?
See, it will not be. But see, at present, what we have the only following information is provided. So accordingly, we can only execute. So if you have more number of columns will be included for different values of alpha, that range can be squeezed. Okay, or else I have told you that instead of that you can use this chi2 CDA function in the MATLAB that will give you the almost near values.
Okay, sir.
Okay. See, whatever the information will be provided based on only you can give the solution. If you need more information, means the person should supply it. How will you identify otherwise? Okay.
Right, sir.
Yeah. Okay. Now this the another natural distribution from the normal distribution is T distribution. It's also sometimes known as student T distribution. Okay, and it's highly applicable in statistics again. So this is again we are going to discuss in a similar manner what we have discussed for the chi-square distribution. Okay, and this is here you can see is defined as the ratio of two distribution. Okay, what for n here n is denoting the degree of the freedom again, and you can see z is the numerator follows the standard normal variate. Okay, and chi-n square distribution with parameter chi-n square, if you recall, chi-n square will follow the gamma distribution with parameter n by 2 comma 1 by 2. Okay, so certainly you know what is the expectation of chi-n square by n. Okay, from here you can identify what will be the expectation of chi-n square. We will go into detail what are the nice properties attached with this t distribution. Okay, right? So chi-n square will follow the gamma distribution with n by 2 comma 1 by 2. So what is the mean? Can you identify what will be the mean? What information I can get from here is for the chi-n square by n, because that is important. Let's go to the next page. So since you have this information, chi-n square follows the gamma distribution with n by 2 comma 1 by 2. So expectation of chi-n square by n is equals to, I'm trying to identify for y equals to chi-n square by n, because this n is here is dividing, and what will happen in the long run, what you can do. So chi-n square by n is equals to 1 by n time expectation of chi-n square, and you know chi-n square mean is n, right? Is going to be mean is 1. Certainly you can find the variance also. Okay, variance of chi-n square by n is equals to 1 by n square variance of chi-n square. That's going to be 1 by n square into 2n. That's going to be, you have 2 by n. So what you can analyze, at least from the variance, as n increase, the spreading is means, or the curve will be more thicker. What means spreading will be less. This variance will tend to 0 as n increase. Okay. Now, what the weak law of large number says. Okay. Since you have chi-n square, you know. Okay. If you have, if you recollect all the previous knowledge. Okay. So since you have chi-n square is nothing but summation of zi square, I is equals to 1 to n. Okay. Each zi is zi square is iid. Okay. They are identically independently distributed random variables. Then weak law of large number says that for every epsilon bigger than 0, probability that, okay, mod of chi-n square by n minus mu greater than epsilon will tends to 0 as n tends to infinity. Okay, using weak law of large number. Okay, using weak law of large number. What it says now? It says that mean, what is mean is, what is the value of mean for this chi-n square by n? Just now we have identified is 1. So probability that this xn square by n is getting apart from 1 for every epsilon bigger than 0. Epsilon you can take however small and however large is tending to 0. So with confidence 1, we can say that chi-n square by n in the long run can be approximated by this one. Okay, as n tends to infinity. As n goes large, it can be approximated by this. So certainly, say whenever you approximate by this one, if you okay, it's an identity function. Okay, constant function. Okay, constant random variable. Now, so this implies square root will also this square root. So this will implies what? This implies in the long run that Tn in the long run will approximately z. Okay, divide by 1 that is there. Okay, approximately a standard normal variate when you have n as tends to infinity. Now I think I have a graph of this. Okay, yes. So you can see in the Tn density function plot, okay, that n equals to 1, n equals to 5, n equals to 10, and it's more towards the bell-shaped curve as n goes to large. Okay, and you can see the thickness is increasing. Okay, right? And further, you can also see that T density with 5 degrees of freedom. You can see if you plot the standard normal density function and T density with 5 degrees of freedom, and you can see how much similarity both the curves have. They are almost, the error is almost negligible. Means, or you can use 6 degrees of freedom or 5 or 7 degrees of freedom, and you can improve your curve. And ultimately, it goes to the converts to the normal distribution. Now, what another important thing is, it's going to be almost, so it's going to be a symmetric about the point 0. Okay, symmetric about the point 0. Okay, mean is 0. Okay, because so that's very easy to get. So in the long run, the mean can be approximated by 0. So this this can be actually established. Okay, you can establish that fact, that expectation of Tn, that mean of this Tn is going to be 0. Okay, that you can establish that result. Okay, by identifying the MZF and all that story you can do. Now, since it is symmetric about the 0, how it will help you? Okay, what is the nice property attached with this? Okay, let's go further. Okay, so I have already discussed this. Okay, here I told you expectation of Tn can be shown as 0 for n greater than 1. N greater than 1. I hope you can. Okay, and variance of Tn can be shown that n by n minus 2 for n greater than 2, and it will tends to 1 as n tends to infinity. So both things can be proven by finding the MGF of T distribution. Okay, you try it. Okay, let's see. Now, similarly, we can also again, this like in the chi-square and normal distribution, we also have T distribution table. Okay, that also will be worked out in the similar manner. Okay, again here n stands for the degree of freedom, alpha stands for the probability value between lies between 0 1, and this alpha is and T alpha comma n, these are related by again with the similar formula. Okay, now this statement you should read carefully. Since T density function is symmetric about 0, therefore minus Tn, if you take the negative of Tn, okay, it also has the same distribution as Tn. Okay, you can establish that distribution function. Okay, you can start with the distribution function of Tn, and or you start with the distribution function of minus Tn, and use the fact that this is symmetric about the 0. You can establish that the minus Tn also has the same distribution. Okay, means in other words, you can show that Ftn of x, or T, you can say in short. Okay, or instead of T, let's say x, can be shown as F minus Tn. Okay, that you can show. It's very easy. Now, once you use this property, what it will give you is the following. Okay, so it implies that probability that minus Tn greater than T alpha comma n is also alpha. So Tn is greater than equals to T alpha n is alpha, and since this is symmetric about 0, that will give you that if you take instead of Tn minus Tn, that also is equals to alpha. Now, if you multiply by minus here and see this inequality will change, and that is equals to alpha. And so what ultimately it gives you, you can follow the slides also. Okay, what it will ultimately give you, the negative of T alpha comma n value can also be identified by T1 minus alpha comma n. Okay, So this is how they are related. So Tn greater than minus T alpha, and what is minus T alpha? Is going to be nothing but, because this here is 1 minus alpha, here is 1 minus alpha, and n degree of freedom. Okay, right. So let's try to see. Okay, this problem. So probability of T12 is less than 1.4. We want to look at this. Okay, so we have this following table. Okay, the t-square distribution table. Okay, so it is also now till infinity it is gone. So probability that T8 less than 2 points. So these are here is given as examples. Okay, that also you can understand from there. Okay, so what you are trying to identify is probability of T12 is greater than 1.4. Means n is equals to 12. So certainly you have to look at the 12th row. Okay, greater than 1.4. So 1.4 value will lies here. So 1.356 and 1.782. You write. Okay, in between there 1.4. So certainly the values lies between. So you have to look at the values again. Alpha equals to 0.10 and 0.05. So the probability value will lie between 0.05 and 0.10. That's easy to identify. So the probability that T12 is greater than 1.4 is lies between this interval 0.05 to 0.1 based on the information we have. Okay, so I think I have this. This is the MATLAB function. Okay, TCDF. This is the second parameter is the degree of freedom, and this is the value of, means this is approximating the area left to the point. Okay, and you want the area right to this. Okay, so that's going to be then 1 minus of that, and then you can find out by using this. Okay, right. The rest of the things will be all are will be in the similar manner. Okay, right. Okay, right. Now, so here is the definition of, because this definition is required uh, for the case of central limit theorem. One central limit theorem will be, I think, okay, we will go till that. Okay. So we have the sample mean notation. Okay, is x bar. So you have been given with a sample of values, which will see sample of values from a certain population. So you may have a large population, or you take your class of 330 students or 300 students. Okay, and you note down everyone has some, you note out their parameter of heights. Okay, what are the height? Or you write down the age. Okay, and or other different parameters. Okay, so you have some sample data. Okay, then the sample mean, which we denote by x bar, is going to be defined as summation of the n sample values divided by n. I think that's very usual. And when you are going to deal with certain data, okay, and you are certainly with, if you are working with a sample of values, so certainly you should understand that, okay, they all will follow they are identically and independently distributed random variables. So it's therefore this information also we are imposing here x1, x2, xn are IID random variables. Okay, let's take, so if IID random variables, let's denote with mean is mu and variance is sigma square. Now, can you able to, so once you have this information, can you at least identify, so x bar is another random variable. Can you able to identify what is the mean and what is the standard variance of this? It is very simple task. Okay, so it's very simple task to identify the mean of this x bar. So you have x bar is equals to x1 plus and so on plus xn by n, where and you have mu of xi is equals to mu for all I. Okay, and sigma xi square is equals to sigma square for all I. This is information is for each I equals to 1. So I hope this information is enough to identify what is x bar expectation, because these are independent random variables, identically independently distributed. So it's going to be 1 by n summation of expectation of xi's. I is equals to 1 to n. So each one is equals to mu n time mu, and that's going to be mu. So mean is still mu. Okay. Now variance of x bar is equals to, I think it's very straightforward, 1 by n square summation I equals to 1 to n. Variance of xi since independent. Okay. So covariances are 0 and so on, that those things can be implemented here. Now sigma square n time. So n times n will get cancelled. So you have sigma square by n. And you can see as n goes large, this tending to 0. So spreading will be very less. Okay. Right. Now, so now I'm ready to give you the center limit theorem, and which will give you the mathematical base. Okay, what will happen in the long run. Okay, so center limit theorem says if you have a sequence of IID random variables, means they could be a sequence you can identify as a uh, data, okay, sample of values, okay, and they all are IIDs. So n number means sequence means is countably many, you can say. Okay, each having mean and variance is sigma square. Then for n large, their summation will follow the summation of xi, I equals to 1 to n. N large. So this is also a very open question. Okay, how large n? Okay, what is the value? What is okay? So general thumb rule is n greater than equals to 30 will satisfy for almost all the distributions. This will satisfy. Okay, that's a general thumb rule. Okay, but it's still a open question. Okay, so for n large, this summation xi, this new random variable y equals to summation xi, will follow the normal distribution with mean is n time mu and variance is n sigma square. What is y? If you try to look at y back, and it's going to be n time x bar. Okay, you know the mean of x bar is what? Mu. So n time mu. So this is here is n time mu. What is the variance of x bar? What was the variance of x bar? Was sigma square by n. So variance of n time x bar is n square will come out, n square times sigma square by n, so n times sigma square. So they are sitting here. So variance of mean of this n mu and variance of this is n sigma square. That information. And what type of distribution it will follow as n goes to infinity is going to follow the normal distribution. Okay. Now, certainly once you have this n large and it follows the normal distribution, certainly you try to change it into standard normal variate and you do all the stuff. Okay. Now, what we can observe from here is another way of representing the center limit theorem in terms of probability. Okay, what it is as follows. Okay, now try to read this. Okay, I'm zooming it, whether you convince yourself that this is an equivalent. case. Okay, can you try to convince yourself, which I stated previously, this information can be translated into this or not? Yeah. Look at here, x1 plus x2 plus xn. This is summation of xi. This n time mu is the mean. Sigma root n is a standard deviation. So what we have done is y minus mu by sigma. Okay. So central limit theorem says that this will follow the standard normal variate. So this is the information only. Less than x equals to is can be approximated by the standard normal variate, probability of z less than x. And this is all happening whenever we are putting all the your you can say obtained numbers, okay, in your mid semester examination or end semester examination. When you have the number of students are more than 100, we are approximately we are getting the almost bell shaped curve. Okay, so the previous information can also be translated into this one. Okay, right? Okay, so let's try to see this problem. Okay, okay, read this problem. This problem states that an insurance company has 25,000 automobile policy holders. If the yearly claim of a policy holder is a random variable with mean 320 and standard deviation 540, it is given to you. Then approximate the probability that the total yearly claim exceeds 8.3 million. Yes. So insurance company has 25,000 automobile policy holders. So if you each policy holder, if you denote by I equals to 1 to 25,000. And if you denote xi as the yearly claim of a policy holder I, okay. So there are how many random variables are 25,000 random variables, and each will follow. We don't know what distribution it will follow, but we have the information that each random variable with mean 320 and standard deviation 540. More than that, each person can be treated as independent. Okay, you claim one person will claim this independently to other. Okay, then in that case, approximate the probability that the total yearly claim exceeds 8.3 million. This is what we want. So what I just now told you, if you translate it, okay, what you will get information is this. Okay, so xi denote yearly claim of a policyholder I, and x if you denote total yearly claim. So x equals to this summation of I equals to 1 to 25,000. And where each xi has a mean mu is 320 and sigma is standard deviation is given to you 540. So central limit theorem says, because see I have told you that sample can be treated as an IID values. Okay, so this x is n is very large, 25,000 policyholder. So this can be approximated x as a normal distribution with mean is n time mu and variance is n times sigma square. So what is n? N is 25,000, mean is 320. So n time mu is 25,000 into 320. N times sigma square. So n is 25,000. Sigma square is 540 square. Okay. So what it will be is this one. So you have the following. So expectation of x n time mu, that's going to be, if you translate into this, 8 into 10 to the power 6. And standard deviation of x is sigma root n. That's going to be 540 into square root of this. And if you translate it, this is going to be this. Now, this information, so mean and standard deviation information will help you to translate this normal variable to standard normal variable so that you can use the normal table. Okay. So this is what it is done here. So what you are interested in, more than 8.3 million. So 8.3 million is which you are interested in, probability that total yearly claim is exceeds 8.3 million. So 8.3 into 10 to the power 6. Now change the information into the standard normal variate. So subtract mean, divide by standard deviation. So this is what this story is here. Okay. And what you will finally observe is you are try to identify what is the probability that z is greater than equals to 3.51. And if you go back and check with the normal table, it's going to be 0.00023. That's the probability. Okay. Right. Yeah. So I think we can. I think we can stop here. If you have any question, you can ask.
Hello, sir.
Yes.